Dear students, myself Dr. Mallikarjun S. Biradar, Assistant Professor in Mathematics, Government First Grade College, Basavakalyan. Now the 60th session of Graph Theory 2. The title of the topic is Results on Tournaments. In the previous session, we have discussed about a tournament and the different types of tournaments with two vertices, three vertices and four vertices. So isn't it? So like that, now we will see some results based on the tournaments. The first theorem on tournament, of course, it is on four small tournaments. As I have mentioned, the small tournaments with the two vertices, three vertices, and four vertices. So those are the small tournaments. So this is the theorem on small tournaments. So what is that? We will see. Even we can verify this theorem with the diagram which I have shown you in the previous slide. That is figure 2 of the previous session. So what is the statement? Every tournament has a spanning path. Every tournament has a spanning path. Means a path containing all vertices of the digraph. Okay. Or if you are considering a tournament with three vertices, there is a spanning path with three vertices. If you are considering a tournament with four vertices, there is a spanning path with four vertices, like that. Okay. So now we will prove every tournament has a spanning path. How to prove the result? So one of the powerful method to prove the result is mathematical induction. So now we prove the result by using the mathematical induction on the number of points. Okay. So if I consider already in the previous session, if we consider the tournaments with the two vertices, three vertices or four vertices, we observed that so those tournaments are called small tournaments. There we have observed such tournaments has a spanning path by inspection. If you are considering a tournament with two vertices, means only one edge between two vertices, okay, A to B. When there is an A to B arrow mark, A to B, or B is reachable from A, okay, or A is playing with B, so there is a spanning path between A and B. If you are considering a tournament with three vertices, okay, either from A to B or B to C or C to A, so like that there is a spanning path containing three vertices. So it is, even you can verify with the four vertices. It implies it is very obvious to verify the tournament with two vertices, three vertices or four vertices. So this will be the inspection. So it helps us to go for the next step. Okay. So therefore what we are going to say in the first step, every tournament with two or three or four vertices has a spanning path. This is by inspection. Okay. Now we assume the result is true for all tournaments with n points. So this is our assumption. Okay. Now we consider a tournament T with n plus 1 points. Our assumption is the result is true for n points. Now we prove the result, or we are going to consider a tournament T with n plus 1 points. So that we have to prove. Let V0 be any point on T. Any point on T. Then T minus V0. What happens if you delete V0 from the T? Then T minus V0. So we have discussed the different subgraphs of the digraphs. So directed subgraphs we have discussed. So there, if you delete the vertex V0 from the tournament T, so what will you get? You will get a tournament T minus V0. So T minus V0 is a tournament with how many vertices? It was n plus 1 vertices. After deleting the vertex V0, we will get how many vertices? So we will get only n vertices, isn't it? So therefore, T minus V0 is a tournament with n points. So it has a spanning path P. It is from the assumption. What was the assumption? The result is true for all tournaments with n points. It implies there is a spanning path. Say P. P is the spanning path. So containing the vertices V1, V2, V3 and so on and so forth, Vn. Okay. Either arc V0 V1 or arc V1 V0 is in T, because already we have mentioned between a pair of vertices either A to B or B to A, not both directions will be there. So you won't get such multiple edges, isn't it? Between two vertices, only one direction, either from A to B or from B to A. So you won't get V0 V1 or V1 V0 in T. So you will get any one. So either arc V0 V1 or arc V1 V0 is in T, because it is a tournament between A to B, one match. You can't say B to A. Obviously A to B is nothing but B to A. So one of the directed arc must be there between two vertices. Okay. So therefore, what we are going to say, if V0 V1 is in T, then V1 V0 will not be there in T. Okay. Then V0 V1 V2 and so on and so forth Vn, okay, is a spanning path, because it is a spanning path with n vertices, because after relating one vertex we got only n vertices by the assumption. So there is a spanning path containing n vertices. So the spanning path is V0 V1 V2 and so on and so forth Vn. So this is a spanning path of T. If V1 V0 is in T, what happens? If V0 V1 is in T, V0 V1 will not be there in T, isn't it? So like that, let Vi be the first point of P, for which the arc V0 V1 is in T, if any, suppose. Okay, then Vi minus 1 V0, so one vertex Vi minus 1 V0 is in T, so that V1 V2 and so on and so forth Vi minus 1 V0 V1 and so on and so forth Vn. So this is a spanning path. Okay, if no such point Vi exists, then V1 V2 and so on and so forth Vn V0 is a spanning path. So in any case, we have shown that T has a spanning path. So that's it. So hence the proof. Okay. So the next theorem is almost similar to what we can say. It is analogous for strong tournaments of the preceding theorem. Okay. For arbitrary tournaments. So what is that theorem? We will see. So every strong tournament with P points has a cycle of length n. So what kind of tournament we are considering? We are considering a strong tournament with P points has a cycle of length n, where n may be 3, 4, like that of P. It implies, suppose it is a tournament with 4 points, then there is a cycle of length maybe with 3 or with 4. Suppose there is a tournament with 5 points, then there is a cycle of length maybe 3 or with length 4 or with length 5. Okay. So again we prove this result by using the mathematical induction. Okay. But on the length of cycles. So we consider the mathematical induction on the length of cycles. If a tournament T is strong, then it must have a cyclic triple. So cyclic triple, in the example we give, what is cyclic triple? Okay, transitive and cyclic triple. Assume that T has a cycle Z, which is V1, V2 and so on and so forth, Vn, V1, because starting and ending point must be same, of length n less than P. We will show that it has a cycle of length n plus 1. Okay, so now there are two cases. Either there is a point U not in Z, both adjacent to and adjacent from points of Z, or there is no such a point. So there are two such cases. Okay, so now we consider the case 1. In the case 1, assume there is a point U not in Z and points V and W in Z, such that arcs UV and WU in T. So without loss of generality, we assume that arc V1U is in T. Okay, so without loss of generality, okay, we assume that V1U is in T. So next, let Vi be the first point going around Z from V1, for which arc UVI is in T, definitely, then Vi minus 1 U is in T, definitely, and V1, V2 and so on and so forth, Vi minus 1 U, Vi and so on and so forth, Vn, V1 is a cycle of length n plus 1. Okay, so the other case 2, there is no such point U as in case 1. Hence, all points of T which are not in Z are partitioned into the two subsets, say U and W, where U is the set of all points adjacent to every point of Z and W is the set adjacent from every point of Z. Clearly, these sets are disjoint, okay, and neither set is empty. So it implies both the subsets are non-empty and their intersection is phi, means both are disjoint sets. Okay, since otherwise what happens, if not, T would not be strong. Okay, so for that reason, these are the two different subsets and both are non-empty. Furthermore, there are points, say the point U belongs to the set capital U and point W belongs to the set W, such that arc WU is in T, is in the tournament T. Therefore, U V1, V2 and so on and so forth, Vn minus 1, WU is a cycle of length n plus 1 in the tournament T. Hence, there is a cycle of length n plus 1. So, this concludes the theorem, or you can say we have proved the theorem. Okay. Now, based on the previous result, there is a corollary. A tournament is strong if and only if it has a spanning cycle. Okay, a tournament is strong if and only if it has a spanning cycle, that is a cycle containing all vertices, all points. Okay, so this is the corollary just based on the previous theorem or result. So already we have discussed what is the definition of directed Hamiltonian path and what is the definition of Hamiltonian digraph. Already we have discussed, even though we are using these ideas for our next result. So let me recall these concepts once again. A directed path, or you can say cycle, in a digraph D is called a directed Hamiltonian path, or you can say cycle, Hamiltonian cycle or Hamiltonian path, if it contains all the vertices. Okay, so it is a cycle containing all the vertices, so that is called a directed Hamiltonian path. So any graph, any digraph which contains Hamiltonian cycle or Hamiltonian path, so that would be Hamiltonian digraph. So what we are going to say, a digraph is called a Hamiltonian digraph if it contains all the vertices, or you can say there is a Hamiltonian path in that graph. So that graph is called Hamiltonian digraph. Okay, so let us consider another theorem. What is that? Every complete tournament has a directed Hamiltonian path. If you consider any complete tournament, maybe with 3 vertices or 4 vertices like that, so that complete tournament has a directed Hamiltonian path. Again, to prove this result, we use the mathematical induction method. Okay, so what we will do, we have verified that complete tournaments with 2 or 3 vertices have Hamiltonian path. Even in the example also, a tournament with 2 vertices, even a tournament with 3 vertices, those are called small tournaments. So already we have verified that there is a Hamiltonian path. So this is the inductive assumption for the proof by induction. Okay, it implies we have verified for 2 vertices and for 3 vertices. So now let us assume the theorem is true for n vertices. Okay, This is the assumption. So based on this assumption, now we prove that the result is true for n plus 1 vertices. Okay, so now we consider G be the complete tournament with n plus 1 vertices. It implies it is like a complete graph with n plus 1 vertices. So if G is a n vertex complete sub-tournament of G, what we are considering from this graph G, which is a complete tournament with n plus 1 vertices, in that we are considering a sub-tournament, that is a small g is a n vertex complete sub-tournament of G. It implies one vertex is deleted. So like that. Okay. If G is a n vertex complete sub-tournament of G, then G has a directed Hamiltonian path because of the assumption, inductive hypothesis. Okay. So the second step what we have considered, we have assumed the theorem is true for n vertices. Okay. So with that assumption, so definitely the small g means the directed graph small g has a directed Hamiltonian path. So in particular say V1, V2 and so on and so forth, Vn. Okay. So now we have three cases in complete tournaments. Okay. There will be three different cases. Which are those? We will see one by one. Case 1, let the arc joining Vn plus 1 and V1. Okay, there is an arc joining Vn plus 1 and V1 be directed towards V1. Now we have Hamiltonian path, that is Vn plus 1, V1, V2 and so on and so forth, Vn of length n. Okay, so the case 2, let the arc joining Vn plus 1 and Vn be directed from Vn to Vn plus 1. In this case, what happens? Now we have Hamiltonian path V1, V2 and so on and so forth, Vn plus 1 of length n. Okay, so this is the second case. So the third case, let these edges joining the vertices, the pair of vertices V1, Vn plus 1 and the pair Vn plus 1. The first pair is V1, Vn plus 1. The second pair is Vn plus 1. Be directed from V1 to Vn plus 1 and Vn plus 1 to Vn. So let Vi minus 1 and Vi minus 1 and Vi be two adjacent points of G. So these are the two adjacent points of the directed graph small g. Now we join Vi minus 1 to Vn plus 1 and Vi to Vn plus 1. Okay, then let the directions be from Vi minus 1 to Vn plus 1 and Vn plus 1 to Vi. Then what happens, you know? Now instead of one edge Vi minus 1 Vi, take two edges. Say Vi minus 1 Vn plus 1 and Vn plus 1 Vi. So what happens? Now take the path, complete path, say V1, V2 and so on and so forth, Vi minus 1, Vn plus 1, Vi and so on and so forth, Vn. So the length of this path in G is n and the number of points in G is n plus 1. It implies the directed graph with n plus 1 points have a Hamiltonian path. Okay, so the following figure, if you observe the following figure, so what we have discussed so far, you will come to know in these two graphs, the different cases. Okay. So here it started with, the first one started with Vn plus 1, then to V1, V2 and so on and so forth. It is V3, Vi minus 1, next Vi and so on and so forth. It is Vn. So okay, similarly the second one, V1, V2 and so on and so forth, Vi, I think it is okay, and so on and so forth, Vi minus 1, Vi, then it is Vn and Vn plus 1. So what we have explained in the previous steps, so that you can see in these two diagrams. Okay, so this is how we have proved the theorem. Okay, I hope you have followed. So with this we are going to conclude the session, of course. So these are the three different cases I have told. So first case, second case and the third case. Okay, so what we have discussed in this session, In this session, we have discussed some results on tournaments related to the spanning path, the cycle of length n, even a directed Hamiltonian path. Okay, so now the topic of tournament, of course, it is very interesting topic. Not only the tournament topic, the entire directed graph is of course interesting and very useful. Okay, but to understand the complete topic, so you have to go through in detail or try to understand all concepts properly. Okay, so the terminology of directed graphs, if you follow all the terminology, then very easily you can follow the results and very easily you can solve the examples based on the directed graphs. So these are the reference books. Already in the previous session also I have told to refer. If you want, you can refer any of the books. Graph Theory by Frank Harari, Graph Theory by Professor V.R. Kude, though this topic is not mentioned, but the other three topics you can refer from the book. A first course in Graph Theory by S.A. Chaudham, and one more book that is Graph Theory by U.S. Upadhyaya. Okay, so these are the books for your reference. So with this we conclude the session of the tournament, and also we conclude the last session of the directed graphs. So in detail we have discussed all the 60 sessions. I hope I have made an effort to make the clear picture of all the concepts of graph theory since from the first session to the last session. So please go through once again properly and try to understand the concepts, then it is very easy to follow the results. So with this we conclude today's session. Thank you.